pores, and then these are the porous membranes. And more recently, there were some papers, since we started to challenge the solution diffusion mechanism, also added ion exchange membranes, and also organic solvent nanofiltration. Now the question, why we have this classification? First, it's historical classification that was decided way back, 30, 40, 50, 60 years ago. And because at that time they did not have any characterization technique to see each membrane looked very dense, no pores. Also, this is before the advent of molecular simulations. Now, through molecular simulations, we can find many interesting phenomena and see that indeed there are some pores. There is also an arbitrary cutoff between a porous and non-porous membrane, as you see here. I want to connect the laser. And lastly, it simplifies modeling. Once you have a dense membrane, you can have really some simple physical mathematical model, and then you see that they apply it almost to any membrane. Now, however, there is ample experimental evidence for the presence of pores in this what we call dense non-porous membrane. Okay, this is just a list, and again, I sent you the PDF of this lecture. You can just click on this, and then you will open the article. Again, there were some studies using pulse, wax, and SONS, these very advanced techniques, and they show pores between 0.5 and 1 nanometer for reverse osmosis and nanofiltration membrane. Even the same group, like reference 4, found that there's some interconnected pore network. Sometimes they are just pores void, but many times they are interconnected. Then they found that in organic solvent nanofiltration inside the membrane, experimentally found there are a lot of clusters. So solvent is clustered, it's not just single molecules. And lastly, for ion exchange membranes, like Nephion, they found a lot large nanochannels, and again by SOX, and between 1 and 4 nanometers. So again, there is ample evidence that membranes are porous, and you cannot find anything that is non-porous. Now again, whenever you talk about pore size, everyone who does research in reverse osmosis, you always talk about pore size. You see all these papers, pore size, every pore size. But then, if you go to some conferences, and for some reason, for these old guards, they immediately tell you, no, reverse osmosis membranes are dense with no pores. And this is more like scolding you. You cannot say. Again, when I was a student way back, if you said a membrane always a pores, they will cancel you. But again, you can ask, but if there are no pores, how water and salt going through? And again, many times they find some simple mechanisms that I'm going to describe soon that really physically are very difficult to understand. Now, this one I showed you, most of the experiments I showed you there were done for dry membrane, but once you wet a membrane by water or a solvent, it's a very dynamic process, and water or solvent will hydrate the membrane or solve it, and then you will expand. You get a lot of pores, and you can do it by molecular simulation. Again, I will show later molecular simulations, that what we call percolated solvent accessible free volume. You just do non-equilibrium molecular dynamic simulation and challenge the membrane with water molecule, and then see where the molecules can go. And you see for all these membranes, like reverse osmosis, all these showing percolated, connected all the way from the feed to the pore side. The color, just for clarification. And this is polyamide and water. Organic solvent nanofiltration, like PDMS with acetone, completely a lot percolated all the way. And even with a per-evaporation membrane, PDMS and ethanol. So showing that beyond this dry membrane, once they are solvated, they can even really very dynamic pore size. Now, generally, when you describe a transporting membrane, they divide it as pore flow model for this porous membrane, again this way in the textbook, which is more like a viscous flow, more like a Darcy type flow, in which the pressure gradient drive the water flow. So this is pressure driven gradient, and of course there's no chemical, no concentration. Again, here I'm talking about the solvent or water, not solute. Soon I will tell you what the difference between solute and solvent and water. So if this is the pressure gradient and there's no change in chemistry, of course the chemical potential is determined by the pressure gradient. And this is described by the classic Darcy's law. Although Darcy's law, those of you who studied in some classes, is found empirically, now you can derive the Darcy's law from the Navier-Stokes equation. You can do Navier-Stokes equation inside the pore, do averaging, and you can rederive the equation. And then there is the solution diffusion model that will spend some time because this is the way the model that we challenge for solvent transport. So the solution diffusion model assumes that the membrane, which is yellow there, non-porous, more like an homogeneous phase. And then the water molecules that are here dissolve into the membrane like partition and then move by diffusion, as you see here. And then it assumes that there is no pressure gradient across the membrane. If this is the pressure in the feed side, it's going the same inside the membrane, as you see here, and then drop abruptly to the atmospheric pressure at the exit. So no pressure drop at all. So if there's no pressure drop at all, then the driving force will be the concentration gradient of these water molecules. Okay, and this is described by the classic fixed law for diffusion, as you see here. Okay, so these are the two models. Now, here I will show you in highlight how they derive this, diffusion, solution diffusion model. In 1917, again, I'll refer to it later in some diagrams. Paul and Elimelech assumed that there is no pressure gradient. And I will show you some reference from the textbook where you can see this derivation if you are interested. And then they did some equilibrium between the liquid phase in the permeate and what's happening inside the membrane. And by some equation using fixed law, etc., they developed the equation for the concentration of water just inside the membrane. CLM is just inside the membrane before going to the permeate. And you see this relationship, and again, with the pressure in the influent, P0, and pressure at exit, PL. What's important here, when you measure the water, when you quantify the water flux by diffusion, remember it's the diffusion coefficient times the concentration inside the membrane at the feed, this is the partitioning coefficient, minus the concentration in the permeate divided by the distance. And when you do some derivation, eventually you get to this equation for the water flux that you see here. And this is the permeance, which is dependent on the diffusion coefficient and partitioning coefficient. Now, a very important part of this equation is, when you look at this equation, this exponential dependence that you see here. Exponential dependence of the concentration at the exit of the membrane on the pressure. Which means if you look at this equation mathematically, at the very, very high pressure, eventually, or when this term is very, very large, this will drop to zero and you get asymptotic flux, constant flux. So in a way, if you plot the flux based on the solution diffusion mechanism for water flow or solvent flow, if you have small molar volume like water, it will be nonlinear and at a very, very large pressure will approach this limit. And if you have large solvent, like organic solvent under filtration, it will approach at lower pressure. Okay? Now, the original derivation, again, what I showed you here by Paul and Elimelech describing this equation here. And again, the only way to derive this equation, they needed to assume that you have a binary mixture where the polymer and the solvent are mixed as a homogeneous mixture. A binary mixture of polymer and solvent. And then they use this equation to describe the transport of a mixture. And they assume that the water is one of the components of the mixture and the polymer is the second component. And this is the equation that they refer to. So before, and you assume that it's completely homogeneous. So now, when I will show you now again, in a way, what you assume here, you assume that the water molecule are more like a gas. They just dissolve as dispersed water molecule and move by diffusion like a gas. But we know that water is cohesive. I'll refer to it later. And again, just a challenge for you. If you have a water here, which is very cohesive, again, the water molecules are clustered, how they can suddenly come inside and become single dispersed? When you go from liquid to single molecule like vapor, you need to put a lot of energy. Where does the energy come from? So it's not. So they assume that also here it's more like a gas. You have gas and enter heat, which is not the case. Now, indeed, we can show that the only time that the solution diffusion mechanism is correct is when you have a gas. And we did some molecular simulations here. You here you have a water as a liquid film. You can have the water here, and there is a way in molecular simulation to make it so it will not move. You put some kind of, call it like a fence, and then these are the gas molecules. So this is more like you think about it, the membrane that's made of water, because the solution diffusion mechanism assumes that the membrane is more like a liquid. Because this, remember, the pressure doesn't change. So the pressure goes from the water side, go inside the membrane, doesn't change. So it's more like a liquid. Only when you have a liquid, the pressure doesn't change. And then you have gas here, and we apply pressure by, again, in molecular simulation, you'll see later when we simulate reverse osmosis, where you put the graphene sheet that you see here, and you apply pressure, and then you create force. And here, for the molecular simulation, we assume that there is vacuum, that every molecule, that gas molecule that reaches at the end, you remove it and you count it. And then always there is nothing there. So you just remove them, so you can count how many gas molecules going through. So this case, like gas in a liquid membrane, fulfills all the classic solution diffusion assumptions that were derived for water, not for gas. And indeed, when we do it here, we see that when we model the transport of hydrogen gas into liquid water, which is, remember, is a liquid water. Again, remember, it's fulfilled the solution diffusion. We have gas and water, like homogeneous. We see this dependence. We see this dependence here for helium and a very, very large pressure in molecular simulation. We see that we follow roughly this equation here. So this was for hydrogen. Now, hydrogen is very small. Let's take methane, which is larger. If it's larger, remember, the nu that you see here is the molar volume. So now the molar volume is larger. So we can get this exponential dependence that you see here at much lower pressure, as you see here, and we can recover this behavior that you see here. Okay? And indeed, when we look at the membrane in the molecular simulation, and again, this is the fit side, this is the permeate side, and this is the hydrogen inside. So the hydrogen was uniform distribution of hydrogen molecules and a clear concentration gradient from the dark blue to here. So this is more like the classic solution diffusion mechanism, but it happens only because we have gas and a liquid membrane. Although my focus here will not be on gas separation, but for example, this is what I showed you for hydrogen and water as a membrane. If you take polyamide membrane, and I will talk about polyamide later, this was happening inside the polyamide layer. You see that inside the polyamide layer, the gas molecules are only in the pores. You don't see this uniform behavior. And the only way to apply fixed law for diffusion, we assume random diffusion, is when you have this homogeneous distribution. So this is more like a side way to show you when the solution diffusion mechanism is correct. And those of you who are interested in the reading of a derivation of the solution diffusion, you can look at this textbook, chapter 2, I give all the derivation, and in our review article, again, it's open access. You can just see all the steps of the derivation in case you need to teach it or whatever. And as an exercise, if you're really interested in it, try to go over the derivation pretending you are going to teach it at the graduate level class, and then I ask you, do the stated assumption make sense to you? And the reason I got into it is eventually I decided to one of my classes to teach the solution diffusion mechanism about 6 years ago, or 7 years ago, and every year that I taught, I was teaching it like in the textbook, but I said, it doesn't make any sense for the water. I cannot understand it. And eventually I said, let's get into it, and this is where I came. Now, I'm talking about solvent, but it's very important to realize that solvent transport is fundamentally different than solute transport. What is solute? Solutes, like ions or salt, they are dispersed in the liquid, and they are dispersed as single molecules. Because they are dispersed as single molecules, you can apply fixed law for diffusion. So if you have any diffusion concentration gradient, they will move by diffusion. Because they are dispersed solute, more like the gas. But when you have liquid, water is cohesive, it's a liquid, it's not a gas. So water, when it goes inside any pores, including very, very small pores, followed by what we call a viscous flow that you know again. And if you remember your other classes, fluid mechanics, you can describe by the Navier-Stokes equation. And indeed, the Navier-Stokes equation, again, I told you, you can derive Darcy's law for porous medium from the Navier-Stokes equation. And even if you have very, very small pores that the continuum breaks down, like the one in carbon nanotubes or in this membrane, you still can describe them roughly by a Navier-Stokes equation type equation when you adjust for the friction and viscosity, etc. You cannot describe it by fixed law for diffusion again. So this is fundamentally liquid always, Navier-Stokes, Darcy, and gases, it can be by diffusion. Now, I will refer to it again, so in this textbook that I ask you also if you want to see the derivation of the solution diffusion mechanism, there is a section 224, and it's titled A Unified View. And they say in the preceding sections, the solution diffusion model was used to describe gas separation, pervaporation, and reverse osmosis. And they said, and again, they found a unified way. Now we can use this simple equation for all membranes. And they decided that all of these membranes are dense. Gas separation, pervaporation, and reverse osmosis. And they said why they did it, because all of them, the driving force is the concentration gradient. And I showed you again, and soon you'll see that indeed it's not. When you get a membrane with liquid solvent, it's more pressure gradient. And as I mentioned earlier, the SD model was also extended to organic solvent nanofiltration and ion exchange membrane very, very recently. And you'll see why they extended it. Now, let's go to the book. Again, this is a 4th edition. This is the book that everyone is using in teaching. And so in the beginning of the book, in the preface for the book, they say, readers of the theory sections, chapter 2 and 3, and elsewhere in the book will see that membrane permeation is described using simple phenomenological equation, most commonly Fick's law. There is no mention of irreversible thermodynamics or anything that is more sophisticated. And then how did he explain it as Stephen? This approach, again, he talked about irreversible thermodynamics, I'll refer to it later, which is classic to describe anything. He talked about this approach as the appearance of rigor, but hides the physical reality even simple processes behind the fog of thought equation. Get a lot of equations there, but again, engineers, we don't need to worry about the equation. And then he said, as a student and a young researcher, I struggled with the irreversible thermodynamics for more than 15 years before finally giving up in the 1970s and then adopting the solution diffusion mechanism. So now let's give you a timeline, which will be more the outline of my talk here. So the first classic study on transport was by Kedem and Kachalsky at the Weizmann Institute in Israel. Again, Kachalsky was a biophysicist that interested in transport in cells, and Ora Kedem at that time was a student, and I think she's now 101 or 100 years old, and she's still alive and sharp living in Israel. And they use irreversible thermodynamics to derive this equation, that the water flux equal to some permeability coefficient times the delta P minus delta pi, and here we have a reflection coefficient. And this model was very, very difficult equation, and eventually, as the author of this textbook said, oh, he gave up on it. And so now let's see. In 1960, Loeb and Surirajan developed the first asymmetric reverse osmosis membrane. This is a discovery that, in my opinion, should have gotten the Nobel Prize, but it's not. And Surirajan always believed that there is a pore flow mechanism, and he wrote it in one of the book and the documents. He did not publish a lot of paper. He proposed the pore flow based mechanism, but everyone ignored it and no one paid attention to it. And then in 1964, Lonsdale et al. First suggested a solution diffusion mechanism or Fick's law for water transport, like what I described to you, and they gave this equation without proof. They just took, it's exactly the same equation. LP is like A, assume that the reflection coefficient is 1, and they gave this equation without proof. Then Rosenbaum and Cotton did some experiment in stacked membranes. I will show you later that they show some that there is water content gradient. I'll refer to this experiment in detail. And they concluded, oh, now we have a water content gradient. It's a proof of the solution diffusion mechanism, and this became really one of the only proof of the solution diffusion mechanism. And then Paul and Albert Lima derived this equation that I showed you earlier by assuming the equilibrium in the interface, no pressure drop, and they derived the equation that I showed you earlier. Now, from 1970 to 2021, which is 5 decades, the solution diffusion mechanism predominated. Once in a while, some people tried to challenge it, but they were killed immediately, and they said, nonsense, no one referred to it. So 5 decades, they decided this is the mechanism of water flow. And again, let's put it here again. This is the 5 decades, 1970 to 2021. And then we wrote our first paper in 2021. It is ES&T, and it's a highly cited paper. Again, this is those who are interested. This is when you look at Web of Science, when you decide if you're a highly cited researcher, you need to have at least 16 of these. So, and again, we presented the solution friction model, and we challenged and said that it's impossible, it must be viscous flow. Then we wrote this paper that I'll refer to you. Water transport and reverse osmosis is governed by pore flow, not the solution diffusion mechanism in sites and vessels. And it's also a highly cited paper. Then we wrote a paper about the physical basis for solvent flow in organic solvent under filtration, showing that also there it's a pore flow. And then more recently we published a paper showing that the experimental evidence for the solution diffusion mechanism, the few experiments, are completely wrong, and I will highlight them. So this is more like an outline for my talk, and if you are interested on historical background for the solution diffusion mechanism and the models, read this one. We have a section 2, and these are the page numbers if you are interested. Now let's start with organic solvent nanofiltration, because this is, you see, the most complicated process, and we can really model it and understand it. We can also describe reverse osmosis very easily. And this was the team that took this challenge. So again, the way we will describe it, I will show you molecular dynamic simulations in detail, then theory, and then experiment. All of them show you that indeed it must be viscous flow or pore flow mechanism. Now, by the way, Jan Wu sent you all the PDF of the lecture, so you can have it there. And so again, simulations were done by collaboration with Ying Li from the University of Wisconsin. He's an expert of molecular dynamic simulations. And the way you do it, we don't know what's happening inside the membrane. Again, there are very, very small pores. There is no experimental technique to know what's going on there. So we cannot continue with this debate, if it's solution diffusion or pore flow, because we can say, oh, we don't know what's inside. We can know what's inside if you do correctly molecular dynamic simulations. And molecular dynamic simulations will give you information what's happening inside. So this is why we need molecular simulations. And the way you do it, you can build this is organic solvent nanofiltration membrane, which is a PDMS membrane. You can build it, you take the chemical recipe the way you do it experimentally, and you can do it by the computer to build such a membrane. And then you verify once you build it that you get things that make sense, porosity, density, based on literature data. Here we put a solvent. I will show you experiments with acetone and methanol. And you put a graphene sheet that you see there, and push the water. The way you push the water, on each carbon atom with a graphene sheet, you apply force, and we apply all the force. It's just like pressure, you push it there. And then on the other side of the membrane, you put another graphene that holds, and this graphene will be at 1 atmosphere, just permeate. And the way to do this simulation, usually it takes a lot of time, so you can do it at elevated pressures. And later you get, because it takes a lot of time, but then you do some few runs at normal pressure. It can take you weeks, and then you see that you get the same behavior, and so now I can do it at high pressure. So this is very common in molecular simulation, because if you don't do high pressure, because the permeation is so slow, it can take you months to get a few data points. Now let's see what's happening there. From this molecular simulation, non-equilibrium molecular simulation, we measure the flux, and then we can see what's happening inside the membrane. So what we see inside the membrane is very interesting. Let's take the acetone that you see here. The acetone, we can measure the coordination number. Inside the membrane, we can take one acetone molecule and see how many acetone molecules are bound to it on average. So this coordination number tells you about the clustering. And okay, so in the feed side and the permeate side, we see at least 15 because it's a solvent, and you get a lot of them clustered. Inside the membrane here, for the acetone, we get relatively large, about 9. And you'll see later why we get 9, because the acetone swell the membrane, get very, very large pores. And most importantly, why we do this clustering number. Remember, the solution diffusion mechanism implies that we have a single molecule. So if you have a single molecule, what should be the coordination number? 0. But we don't see 0 here. So it means it's clustered. It cannot be gas-like diffusion. Methanol, soon you will see, methanol, it doesn't like the PDMS. PDMS is very nonpolar. Methanol is polar, they don't like each other, so it shrinks the membrane. This is why the clustering coordination number is smaller. It's about 4 compared to 9 here. Because acetone likes the PDMS, swells it. Methane doesn't like the PDMS, shrink it, and you get lower clustering number. But the key thing that here, the solution diffusion mechanism requires dispersed single solvent molecules, i.e. a 0 coordination number, which you do not get here. This is one proof that it doesn't work. Then we see if this is the membrane here, again, you can think about molecular simulation as an experiment at the atomic level that you cannot do, but this is an experiment that describes accurately the physics. And we see that naturally what we measure inside, you can quantify, and you see pressure gradient. You see that with acetone, pressure gradient across the membrane. Remember, the solution diffusion mechanism assumes that there is no pressure drop, uniform. And the same thing here. With methanol, we see pressure gradient as opposed to the solution diffusion mechanism that assumes constant pressure. So another proof that it cannot be a solution diffusion mechanism. And by the way, no one did any simulation that can show that the solution diffusion mechanism exists for solvent and polymeric membrane. So again, remember, this is experiment. You don't tell the molecular simulation, I want you to show me this. This was the outcome. Also, we see something very interesting that will explain some of the experimental evidence for the solution diffusion mechanism. We can measure inside the membrane, again, the shaded area, what will be the density of the PDMS, the polymer, going up. And because the density going up, as you go further, moving toward the end of the membrane, it's more compact, you will have less porosity or less solvent. Here we measure the solvent gradient, how many solvent molecules inside the membrane. So they drop. Now, when our postdoc did his experiment, because before we did reverse osmosis, we did not see any solvent gradient, but here we saw a gradient, so he was scared. He said to me, wow, it's a solution diffusion mechanism. No, I will show you soon. It's all because of compaction, and I will talk about it in detail. So what's happening here? Here I'm showing you the pore size distribution of the PDMS membrane with acetone at different pressures. Now, a lot of numbers here, but I will guide you through the lines here. When you increase the pressure, the large pores are compressed. And if the large pores are compressed, now you will have more pores, smaller pores, and this is why they go up, more smaller pores. And this is due to compaction. And the compaction, as I'm going to describe again and again here, when you have flow through the membrane, you will have a pressure gradient, but the compaction pressure that will define very soon will increase as you go along the membrane. The farther you go toward the permeate, the greater the compaction pressure. Okay? So the solvent content gradient that you see here, this is solvent content gradient that you measure how many molecules in each segment of the membrane, is due to compaction, not the driving force for solvent transport as implied by the solution diffusion model. And this will be a big part of my lecture, as I'm going to see soon. So now molecular simulation tells us that indeed it's viscous pore flow. Now let's show you here a theory that described in this paper, a very complicated theory that we needed to collaborate with this expert in collaboration, Martin Jessusveld from Wetsus in the Netherlands. And here we model, if this is the membrane, there is a pressure gradient across the membrane. And soon I will tell you that when we describe the compaction pressure is always the applied pressure minus the pressure of the solvent inside the membrane. So as we move here, you see this area, this is the compaction pressure, and it's much larger here. So we take a small element and we apply force balance. This is the compaction pressure, and all the forces inside the polymeric membrane with the solvent. And this is what we call the extended Flory-Renner theory. We extended the Flory-Renner to assume an elastic polymer membrane and PDMS. Some of you are polymer chemists. I know you are polymer chemists. You understand. So the compaction pressure is balanced by 3 types of pressure or contribution. One of them is the volume exclusion. Because of the finite size of the polymer, we call it volume exclusion. And here we use a more sophisticated expression than the one that Flory and Renner used. Then we have affinity pressure. The solvent interacts with the polymer, and this causes either swelling or shrinking. And then elastic pressure. As you push the membrane, you have elasticity. And here we assume a nonlinear elasticity with a finite stretching up to a certain limit. Because if you take the Flory Renner, it's stretched forever until you eventually tear the membrane. We put a finite stretching. And it's balanced by this equation. Now, let's see what we can get from this interaction. Suppose that there is no pressure. Okay. Compaction pressure happens when you have flow through the membrane and you have pressure drop and then you have compaction pressure. Let's take this element and assume that there is no pressure, just at equilibrium. We take the polymer membrane and see what's happening at equilibrium with the solvent. And what you see here, you see the term of this pi affinity, very interesting behavior. The solvent polymer affinity significantly impacts the porosity of the membrane. So from the simulation, again, we can model this part, and we have a parameter more, not exactly, but similar to the chi parameter in the Flory-Higgins theory. And if this parameter is negative, it means it's solvophobic, doesn't like the polymer, in our case PDMS, and in this case it's solvophilic, doesn't like it. So what we see here, if it's solvophobic, like the example, methanol and PDMS solvophobic, remember we got lower coordination number because you shrink the membrane. And when you go further, if you go positive value, it's become solvophilic, and this was the case for the acetone. For the acetone, I got coordination number, I think, of 9 compared to 4 or 5 for the methanol. So now we can predict sort of like the membrane. Again, it's very dynamic process. The membrane is shrinking and swelling in organic solvent nanofiltration. I'm not, again, some of you probably are not working on organic solvent nanofiltration. It's used to separate organic solutes that are soluble in organic solvent. So similar to reverse osmosis, but again, reverse osmosis use water. Here we use organic solvent because many high-value organic, solutes are soluble in organic solvent. So we need this solvent to operate the membrane. And here I'm focusing in organic solvent nanofiltration on the transport of the solvent, not the solutes. So okay. So now let's see now from the theory that we derive from the extended Flory Renner. Let's look at the porosity or across the membrane. We measure the solvent content. Remember, we showed the simulation gradient because of the compaction. And when we use our theory, Flory Renner, with the right viscous flow through it, we get exactly the same behavior. So our theory shows excellent agreement with empty simulations. And porosity decreases in the direction of flux due to the solvent transport-induced compaction. Compaction always increases as you go here, because as you go farther, the compaction pressure increases. It's always the applied pressure minus the pressure inside the membrane of the solvent. So now we have theory, simulation. Let's talk about experiments. Experiments, we did experiments with PDMS membrane, which is very commercially a state-of-the-art membrane that used in organic solvent nanofiltration, and 6 solvents, 4 alcohols, and 2 other compounds that you see here, and pay attention to their size. Okay, and use that nanofiltration. Now, by the way, I mentioned about organic solvent nanofiltration. Now, there are a lot of research in the field to use organic solvent nanofiltration to separate crude oil. The way we do it nowadays is by distillation, which is very energy intensive, and they're trying now to have organic solvent nanofiltration to filter these all different crude oil components, which will save a lot of energy. Now let's look at the experiment. We do flux versus pressure. See here, okay. Flux versus pressure that you see here for methanol, ethanol, hexanol, and propanol. Here only the alcohols. And we see flux increases and some curvature because of compaction, and our theory fits the data very well. The only fitting parameter that we need to have there is just the chi the affinity parameter because there is no theory to calculate it. Now let's see what's happening with the other solvent. And you see very interesting behavior. Look at this. Look at the scale here. Up to 400 is up to 15. Now the propanol that you see here, you see the propanol is here. Methanol was below. Methanol is like almost zero here. But look at hexane. The flux of hexane is orders of magnitude higher. How can it be? Hexane, the size is 0.43 nanometer, and methanol is only 0.36. The reason is because the membrane swells significantly with hexane. Hexane is solvophilic, likes the PDMS. Expanded, this way you get very, very high flux compared to the methanol that was below the propanol that shrink the membrane. Okay? So this tells you that fluxes do not correlate with solvent size. And theory can fit well experimental data. Now why I'm doing this organic solvent nanofiltration? Because it's much more complicated than RO. RO is only water. And you see that RO doesn't swell because it's cross-linked. And if you can figure out what's going on in this membrane, it will be easier to understand. But again, we did the opposite order. The first paper we published is in RO, and the second one on organic solvent nanofiltration. Now another behavior that quite intriguing, here we do a mixture. Let's have a mixture 1 by 1 by weight of acetone with any of these alcohol. Here acetone and hexanol, acetone and propanol, acetone and ethanol, and both of them 1-to-1 mass ratio. You mix them and then have experiment through the membrane, and this is the flux that we get. This is the flux only with acetone, single solvent, and this is the flux only with propanol, single solvent. And we can fit the data, little curvature, by assuming, by fitting it to the affinity parameter, and always the affinity parameter that we get was in the range between the acetone and propanol, for example. Now, let's see what's coming out of the membrane. What we find strikingly, I mean, really dramatically, if you look at the acetone to alcohol selectivity, what's the selectivity? Would they appear at different selectivity? So this is, you see one, and this is the expression with acetone and methanol. Another experiment, acetone and ethanol, and we did experiment at many different pressures, all the way from 5 bar to 30 bar. And all of them you see here, around 1. Look at the scale here. There is no selectivity. Both of them appear exactly the same chart as seen here. So no selectivity in a 1-to-1 binary mixture of acetone with the various alcohol. All appear together, and they appear more like a, what you call unified fluid. Now remember, the solution diffusion mechanism assumes that you have partitioning or solubility, which will depend on the type of the membrane and the type of the solvent, and the diffusion inside the membrane. So it means that because these are very different solvents, they should have selectivity, because the equation for the solution diffusion mechanism, the permeability equals solubility times diffusivity. And each of them will have different solubility and diffusivity, but we did not see any selectivity, which means they flow as a viscous flow, as unified fluid, and all this concept of solubility times diffusivity doesn't work here. So this is another very strong experimental evidence. Now, we further, in our first paper on reverse osmosis, we took reverse osmosis membrane and also did experiments with different solvents. You can do experiments with different solvents. And we derived this equation for the permeance, or the permeability, thickness-dependent permeability is equal to the pore size here of the membrane times the difference in the pore size and the solvent. D naught is the size of the solvent, size of the membrane, and 1 over viscosity. This is the viscosity, 1 over viscosity, and this relationship. And we took polyamide reverse osmosis membrane that used for desalination and did experiment with water, again number 1, but also other solvents. And we saw that this relationship that we derived here, again, roughly a good relationship you see here. The same thing again with cellulose triacetate. This is the old reverse osmosis membrane, the first one that we derived. We see this relationship, which tells you that indeed it's 1 over viscosity, which is more like Darcy type relationship. And if you have membrane with very, very small pores, the size is also very, very important. Which again, the solution diffusion mechanism assumes any size because there are no pores. And just by affinity, you can partition or solubilize into this homogeneous polymer phase. So permeance in RO membranes is governed by solvent molecule and pore sizes, as you see here. And later we did molecular simulation with, again, Ingli is an expert on molecular simulations. And with in this paper, also we tested if this equation also valid when we get these molecular simulation fluxes. We did simulation of, again, non-equilibrium MD simulations. 16 different members with different pore sizes of fractional free volumes, different polymers. And then 15 different solvents with all sizes, kinetic diameter from 0.26 to 0.69. And we got very good correlation to this equation. And more importantly, we got if the solvent larger than the pore size, it will not go through the membrane. Remember, the solution diffusion mechanism assumes that everything will be solvated into the membrane. But if the pore size is small enough, solvent will not enter. It just happened in reverse osmosis that the pores are slightly larger than the water molecules that can enter. But if you take big solvent, it will not be able to enter anymore. So this is what we call sieving, and sieving is not captured by the solution diffusion mechanism. Also, we analyzed in a recent paper a bunch of data of different kind of membrane, graphene, inorganic, covalent organic framework, polymer, polyamide, all kind of them. And all of them we find that the permeability depended on 1 over viscosity. Again, 1 over viscosity is exactly what Darcy's law predict. So permeance is proportional to 1 over viscosity. And remember, as I told you before, Darcy's law is not empirical. It was derived, can be derived from the Navier-Stokes equation. The same thing if you take advanced transport phenomena, we know that Fick's law was derived empirically initially, but now we can derive it theoretically. The same thing here, if you take a porous medium and you take some volume element inside, and you do all the analysis of Navier-Stokes equation and do the averaging, you can rederive and get exactly Darcy's law. So again, so don't be confused that Darcy's law is empirical. It's really, really describing the fundamental of viscous law. Okay, so this is about organic solvent nanofiltration, which is very difficult. It can swell, it can shrink, and you have solvent of different sizes. Let's go to the case of just water, which is one solvent in reverse osmosis membrane. And this was the first paper that we published in Science Advances. Again, and these are the authors. Again, postdoc Lee Wang is now a professor at Tongji. Jin Long was a postdoc of Ingli, and Han Qing is my postdoc who just started a faculty position in Peking University in March, and this myself here. Now we start with molecular dynamic simulation. I told you why we need to do molecular dynamic simulation. But before, for the polyamide, Ingli is a really expert. He has a lot of papers on polyamide simulation. And whenever you build a membrane by molecular simulations, you need to test and see if it's real a membrane that describes a real membrane. And what we have done in all these papers here, we show that the membrane density from the polyamide simulation fits very well experimental data. Pore size distribution also roughly with fit the experimental data that you determine from pulse method. Atomic composition fit the data, water swelling fit the data, water permeance, so really fit the data. And more recently, we showed that the effect of pressure or partitioning of salt into the membrane, we can simulate the data, and compression. So it's important, and again, in the paper here, Ingli here, those of you who are interested in molecular simulations, he compared many, many force fields. Again, for every simulation, you need to have the right force field, and he compared and he screened all the force field and showed that when you choose the right force field, many of them will give you the same results. But if you choose the wrong force field, you can get very strange behavior. Okay, so again, this thing you see here, similar to what we got from the organic solvent nanofiltration. We find pressure gradient. Remember, the solution diffusion mechanism assumes no pressure gradient, uniform. So this is one strike of the solution diffusion mechanism. It's not correct. Then, here we show no water content gradient. Remember, for the organic solvent nanofiltration, we show little content gradient because of compaction. But because polyamide is highly cross-linked, even at this pressure, doesn't compact. The pores are so small, you cannot compact them. And if you get any compaction, you cannot really distinguish it. So remember, the solution diffusion mechanism assumes that you have water concentration gradient. we do not see any water concentration gradient here. So another strike for the solution diffusion mechanism. Also, remember the solution diffusion mechanism assumes that at a very high pressure we get this asymptotic behavior, and eventually it stabilizes in a sealing flux. That but when we do the molecular simulation, they're all very, very straight, even at very, very high pressure. So we do not see this solution diffusion type nonlinear flux. Another strike. And then water molecules travel through by clusters, like what I showed you in organic solvent nanofiltration. Remember, this study or solution diffusion mechanism assumed that you have more like a gas-like diffusion, that they diffuse a single water molecules or coordination number of 0. You have water molecule and nothing around it. You cannot count anything. And here we saw the same behavior that we saw in organic solvent nanofiltration. This is the feed and permeate, high coordination number. And inside the membrane, even though the pores are very small, we get a coordination number between 3 and around 3 or 4. On average, again, some pores will have more, some less. So it's clustered, it must be viscous flow because solution diffusion mechanism assume 0 coordination number, nothing around it, it's just single molecules. Another strike. Then water molecules travel as clusters through the transiently connected pores. And let's now track the trajectory of a group of water molecules. We took here a group of many clusters of water molecules, and through the simulation, we simulate what's happened to them. And again, the pores in reverse osmosis are all free volume, connected, disconnected, but on average, you have many, many times that you have pores that go all the way. And many times you have pores that are not connected at all, free volume, again, like in polymer science. And what we see here, when we track all of these here, they all go, and we saw all these clusters of water molecules go together. They are not dispersed. We do not see that it suddenly becomes single water molecules. And so water molecules in the group travel together in clusters along the membrane. They are not dispersed. And as long as the time scale for the pore, again, these pores, some of them are transient, as long as the time scale that you have the pore percolated all the way greater than the time of transport, we can see like it's really more like a pore flow because the pore exists enough time for the cluster to go through. And sometimes you have some pores that are not connected, so the water will not go there, it's stuck there. So, okay, so this is another strike with the solution diffusion model. So now we showed for organic solvent nanofiltration, again, it's a viscous flow, the same reverse osmosis, but remember the unified theory in this textbook, they said let's apply it also for pervaporation membrane. Now, I don't know if you know it's a pervaporation membrane, but again, it's a polymeric membrane in which you apply vacuum at the permeate size, and you have some solvent, for example, water and ethanol, that you go there, and eventually you separate it. For example, if you want to dehydrate ethanol, you let only the water go through, or the ethanol, so you have only water. And it's applied by Evic vacuum, and the solution diffusion mechanism assumes that if you have the membrane, the water will partition, move as single water molecules, and when it goes to the permeate side, it will become vapor. So we said, let's check if this unified approach works, and we found that it did. It's flawed. And this paper was published very recently. Non-equilibrium molecular simulation revealed a pore flow dominated transport mechanism in pervaporation membranes. This is the link for the paper, and let's see, we simulated molecular simulation of the membrane. We apply vacuum on the other side, again by molecular simulation. Here we have a solvent, mixture of the solvent. In our case, we're let's see, ethanol and water. No, I think here was just ethanol. Ethanol, and this will be atmospheric pressure because you don't apply any pressure, you apply vacuum here. And what we found, interestingly, that the membrane, in the membrane inside, you will have some, again, it's described here. Up to a certain point, it's a viscous flow. You have clusters, and then at a certain point in the membrane, when the pressure become equal roughly to the vapor pressure of the solvent, in our case ethanol, it changes and becomes single single ethanol molecules. So it means that up to this side, it clusters more like a viscous flow, and here there are single molecules that diffuse inside the pore, but do not diffuse through an homogeneous polymer phase, diffuse through the pore, as you see here. So again, these are clusters. We simulated a membrane of 10 nanometer thickness, and about 6 nanometers, suddenly they became all single ethanol molecules. And this, of course, is not captured at all by the solution diffusion mechanism, which assumes that the water molecule just flow by diffusion all the way, again, implying that if by diffusion they must be not clustered by single molecules, and then when they reach the end, they become vapor. Okay? So this is quite and then we did experiment again. Evaporation can also use for desalination of very high salinity brines. So here we simulated salty solution for water, and we found the same behavior, that the water up to a certain point is clustered, viscous, and then beyond a certain point it becomes vapor and float by vapor, the same thing that we showed here. So for the water, and then become vapor in the latter part of the membrane. Now this is not new. Indeed, phase transition was suggested before by several membrane scientists. Again, Takeshi Matsuura, he was a student of Surirajan, which is the one who discovered the cellulose acetate membrane, and he proposed it in 2 papers way back, but no one listened to him. He said that without any proof, he said that it must be a 2-phase again, that you'll have some part again liquid and some part vapor again, but no one listened to him. Again, another recent paper here, not recent indeed, from 2010 by Neil Chong. He used to be, I'm not sure if he was the main author, also proposed a modified pore flow model for evaporation for transport that include what I found by molecular simulation. And more recently, about the same time that we published our paper, the same time, paper in Nature Communication for desalination membrane found exactly the same thing. A liquid vapor, and then at a certain point the membrane becomes vapor. But then, although they found it by molecular simulation, when they try to model it, they say, oh, it's also, they say they derive what you call modified solution diffusion mechanism, which is incorrect because I showed you that it cannot be. So it's very, very important because the solution diffusion mechanism is ingrained in the head for 60 years. People work on it in a textbook, the people just automatically refer to it. And again, step by step, as I'm showing you, it really, really doesn't work. Now, always when we publish paper, again, usually the people who proponent of the solution diffusion model, again, there are not many of them, but again, they say, oh, we don't believe you need experiments. So in that paper, it was only molecular simulation, but we came up with a very elegant experiment I'm going to describe you to prove that there is phase transition. Let's take a membrane and we apply EIS. I'm sure many of you work with EIS. I see Sean said yes. So you put one electrode here, the other electrode on the other side, and then this is the membrane. Let's take some water and put electrolyte, because salt will have conducting. And what's happened if you apply vacuum in? If you apply vacuum, based on our molecular simulation, there should be phase change. So this will be wet with the ions, but now when you have become vapor dry, you will not have any ions here. So you should get high resistance because there is discontinuity of this conducting. Now here you have vapor water, but the ion cannot be there. Not conducting, you should get very high resistance. And if you turn off the vacuum, immediately all the pores will be filled by electrolyte, you should get low resistance. And indeed, this exactly, we are now working on it and modifying it and hopefully write a paper. So this one is fresh from the oven. So indeed, this is the resistance versus time. When you apply vacuum, very high resistance because now we get this vapor with no ions, it doesn't conduct, super high resistance. When you turn off, it fills immediately, and you get zero resistance. And again, up, vacuum, it's raining outside. So, so up, vacuum, phase change, we get high resistance, closing, low resistance. So it's very, very convincing. Then you can also measure the phase, the angle. And here, when you have a vapor and liquid, you have this vapor-liquid interface, and the phase, you see minus 40 degrees. It means that you have an interface. This shows you some capacitance. But when everything is full of electrolyte, when you do not have any vacuum, it's conducting, the angle is close to zero. So this is really an amazing experimental proof that we get this phase change. And a simple equation of the solution diffusion mechanism cannot explain it. Again, no way you can explain it. Okay, good. Now going to the last part of my talk. Still have energy, so and then we'll have the question at the end because it's recorded. And now I'll talk about the critical evaluation of the experimental evidence of the solution diffusion model. And we just published this recent paper. So the first experiment in 1969 was by Rosenbaum and Cotton. They took 5 cellulose acetate film. They were not reverse osmosis membrane. Cellulose acetate film, they stacked them, put them in a reverse osmosis cell, measured the water flow through them, and at the end of the experiment they stopped, open it, and measure immediately the water content in each film. So this is what they found. Again, these are the film, and experiment at 68 atmosphere, they found, again, this is the data. And here, higher pressure, this is the data. So they find some water content gradient, look at this. But it's not very high. See, it's 0.01, 0.011. There are no error bars here, but again, in those days again. And they did not provide any information about the membrane, the pores, anything. And since then, this became a textbook material. They said this is the proof for the solution diffusion mechanism, and this is appear in this textbook again as a proof. But let's go back to this compaction pressure. In 1971, again, we did not know about this paper, only after we published the first paper, and later we found this paper and said, oh wow, this explains everything. Petterling proposed a simple model for the compaction pressure in which, if this is the membrane here, this is the pressure of the solvent inside the membrane. So the difference between the pressure in the feed and the pressure of the solvent inside, this difference is what we call the compaction pressure. And the compaction pressure you see here in green will be equal to the applied pressure minus the pressure of the solvent inside the membrane. So when the solvent reaches the end of the membrane, it's of course, atmospheric pressure. The pressure is zero. So delta P minus zero, it means that the compression pressure is delta P at the end, very, very much. And at the beginning, it's zero because you have delta P minus delta P. So this is one, and again, I showed you already that molecular simulations of the organic solvent predict these kind of things, and also our theory that I showed you earlier. So the pore-free volume decreases from the feed side to the permeate side. And this is the paper, the original paper, influence of compacting pressure. Again, luckily we found it, a few years ago, and it explained everything now. So again, let's look at the data from Rosenbaum and Cotton. They measured this water content gradient. Again, these are the membranes. They stacked 4 of them. And again, this is the hydrostatic pressure inside the membrane. This is the compaction pressure, increases along the membrane. And when we fit it to our model, even in this paper, we simplified the model to make it more simple, that you need only 2 parameters. You need to know the initial porosity and the coefficient of compressibility of the polymer. And we fit the data very well by compaction, beautifully. We only fit the data very, very well. So there was another experiment. Again, these are the proponent of the solution diffusion model. UT Austin, again, the solution diffusion model, Don Paul was in the UT Austin that derived it over 50, 60 years ago. And now they did experiments with 6 stacked Nephion. Nephion is ion exchange membranes. They stack them here, and then measure the water flux going through the membrane, and stop it, and immediately measure their water content gradient. And they found this water content gradient here, of this stack, more like the way that was found by Rosenbaum and Cotton in 1969. And they claim, because of this water content gradient, this provides the driving force for diffusion, and this must be a solution diffusion mechanism. Now here they are talking about ion exchange membrane, which before no one thought that they are dense and non-porous. And when we analyze, look at the analysis of these membranes. They reported the water flux, and we can calculate roughly what will be the pore size. And these are the permeabilities of different membranes. Seawater RO from the literature, brackish water RO, NF, and UF. So this Nephion fits here. It's more than 1 nanometer. So now the authors extend the solution diffusion mechanism to IEM membranes, which typically have pore sizes between 2 and 5 nanometer. Just because of this experiment that show you the water content gradient. And soon I will see I will generalize it, and you can get this water content gradient for any membrane, including microfiltration membrane. So again, we use our pore flow with compaction model, again, the one that I showed you earlier, and we can predict the data beautifully. And indeed here we needed only, indeed with no fitting parameter. They reported the initial porosity of the membrane, this is what part of the model, and then we took from the literature for this membrane the coefficient of compressibility, and we were able to fit the data. Now let's talk about this experiment again. Now at my postdoc we got into it very deeply. This experiment, you take the membrane at the end and measure the water content. So is it diffusion or compaction? Based on the solution diffusion mechanism, when you apply pressure, you get this gradient of these single water molecules just because of the pressure. You know, Don Paul and Elimelech called it pressure-induced concentration gradient. They did not talk even about water content gradient, concentration gradient. So you apply the pressure, you form it. So what happens when you relax the pressure? If you now have no pressure, it should be eventually equilibrated. Look at this. So again, under the solution diffusion mechanism, water concentration gradient relaxes quickly following the pressure release. If you create this pressure gradient, and if you relax the pressure, all the molecules diffuse, and this is what you see here. We simulated based on the equation in the paper of this group, in this paper that I recited, and we see that roughly after about 8 to 10 minutes, there should be no water content gradient, because all the molecules will diffuse and indeed, our model, again, the solid line is our code, and the dashed line is what we have in this paper. And the reason they showed this one in that paper, they showed that they need to measure quickly the water content gradient, so because you will have some phenomena. And so what they did, again, you need to have quick disassembly. It's not easy. You need to have several students help you taking it, and each one measure the water content gradient in less than 1 minute. And they found this water content gradient, that you get the same data that I showed you, but this is from the original paper. But they omitted this point here, because this point here, the last one, based on this model, should be a high. They omitted it, although in the supporting information they provided this number, and it was roughly about here. Now, let's go further. So if the concentration gradient should be eliminated after about 8 to 10 minutes, we can do experiments, and then relax the pressure, wait 10 minutes, and then measure the water content gradient. So this is what we have done. We take the Nephion membranes and waiting for more than 10 minutes, and after pressure release. So after pressure release, everything should relax and the molecules should diffuse and get homogeneous. And again, there is a video, we recorded everything, it's not published again, it's work. So we should have no concentration gradient if the transport follows this classic solution diffusion mechanism, because the single water molecule will be diffused and we get, but we see water content gradient. Again, this is the experiment first experiment, then we did another experiment to repeat it with new membranes, and we got this one. And indeed, the last film that was not reported in this study, it was not reported here, we reported it, and we get it here. Based on the model, it should be, if you look at the model here, based on the model, last data point should be here. So it's very, very clear. The porosity gradient measured reflects irreversible compaction, not a concentration gradient driven fixed diffusion. It's another very, very important evidence. Now, these experiments can be misleading because they concluded that the ion exchange membrane now are solution diffusion type membrane. But I can show you can take any membrane, do this experiment, and you can conclude that every membrane will be solution diffusion membrane. So So if I ask you water transport in microfiltration, we know that it should be pore flow and viscous flow. So we did this experiment with microfiltration membrane, 0.025 micron. The same experiment, stacking 6 of them here, measuring the flux, and then taking out and measure the water content gradient. And we see even in microfiltration water content gradient. So can you say now, based on this experiment, that also this one is a solution diffusion mechanism? No. So this is a experimental evidence. Based on this one, you can classify every membrane. So water content gradient is very important. Is a result of viscous flow, not the cause of the viscous flow or the drive for water flow. Because you have viscous flow under pressure, you get this compaction, you get water content gradient. It's not the driving force. Now, another experiment. I'll show you that water can flow against the water content gradient. Let's stack membranes, and this time, look at the way I stack it. Look at it carefully here. Yeah, go, look here. We put it in the beginning, very small pore, 0.025 micron, then 2 other 0.05, and 2 other of 0.1. We measure the water, the flux, and we measure the water content at the end of the experiment. And we see water content going the other way. So now you can say, but we still measure water flux. So if this water content gradient is the driving force, we should not get the water flux. We should go water going the other direction, but we still get it here. Now to make it even more, again, so pressure driven viscous flow of solvent regardless of the water content gradient. And those of you who are interested more in compaction, and compaction become a hot topic, everyone is jumping into it. This paper we really have the nice model by Anching, Fan, and experiments, and well done, So I will not get to the details, it's here. Now let's show you something another more striking, that you realize how unphysical is the solution diffusion mechanism. Suppose I design a membrane with conical pores. If you're a good material scientist, or suppose I take a membrane and design it with conical pores. This is the membrane, and you have conical pores. Now let's zoom on it. So this is the pores here. Now, based on this experiment, this is a water content gradient, am I right? You have more water here than here. Because they just, imagine you can divide it just to several membranes. You can have much more water content here than here. So there is a water content gradient here. So, and these are sub-nanometer pores. So we establish a water content gradient here just because you can think about it more like a membrane that is that you can design it. So without even pressure, no pressure. So the question, will water flow through the membrane? Because there is a water content gradient. Is it true? There's water content gradient here. Of course the water will not flow through the membrane because you will violate the laws of physics. And here, ChatGPT. So impossible. This will be perpetual motion machine of this first kind. So water will flow with no energy at all. Doesn't make any sense. So another thing that this water content gradient, you can get very erroneous result. You can, based on this, you can say that microfiltration is a solution diffusion mechanism. Based on this, you can think I can generate a membrane that doesn't produce no energy, and you can get water flow. Now, another evidence I told you, and I'm getting toward the end. Another evidence was that you get this non-linear flux behavior. Remember, because of this solution diffusion mechanism, that you get at very, very high pressure, you get constant flux. And this was again from the same group, Paul and Ebra Lima from UT Austin. And again, they published this paper with a rubber film of 254 micrometer thickness, and measured with organic solvent, iso-octane, and cyclohexane. And again, in the book of Baker, this is a classic book that everyone referred to. They showed this data and they claimed this is another proof for the solution diffusion mechanism because we get this sealing or limiting flux at very high pressure. So now let's analyze this data. And again, this is because remember this equation at very, very high pressure should be eventually reach this value here. Let's analyze again these membranes. I'm getting toward the end now. Membranes are highly porous. Again, this membrane that is here are highly porous with pore sizes in the range of tight UF membranes. So they reported the water flux through the membrane, and then based on the water flux and viscosity and the solvent, we can estimate the pore size. And with the isohectane, we estimated the pore size of more than 2 nanometer. And with cyclohexane is more than 3 nanometer. These are very, very large pores. Again, we never thought about them in solution diffusion. And more striking, they reported the data. They reported that with isooctane, 0.66% volume of the film was by solvent. Was very, very highly swollen. Only less than 40% is the polymer. Very highly swollen, and with the other solvent is 0.7. Super highly swollen. So imagine this super highly swollen membrane with such large pores. How can we have solvent transport by diffusion under applied pressure with such a highly porous structure? This is more like the range of tight UF membrane that we all know, the pore flow model. And indeed, if you think further, if you took fluid mechanics and advanced fluid mechanics, you know that the fluid mechanics on the momentum, again, there is momentum dissipation and by the friction between the solvent layers and the solvent and the membrane. So if everything flows by diffusion, how you can dissipate all this pressure? Go by diffusion, you have this very high pressure. What's happening when you get to the end? So it's impossible to understand it. So, and we of course can fit it with a viscous flow with compaction. Again, when you have compaction, you can fit the data beautifully here. So, indeed, when Don Paul published this paper in he published later in 1973 more, he published a lot of papers that become in 1973, showing this concept of the swollen rubber fields and claiming that everything is by diffusion, and this hydraulic permeability is diffusion caused by diffusion. This brilliant guy, Pertolin, he used to be, again, he's passed away way back, but he's a brilliant polymer physicist. And he wrote a comment, a masterpiece comment about 10 pages on the paper, and practically showing that completely everything is wrong. And he wrote here, in a way, again, the perpetual machine is not my invention, I took it from him. He claims that whatever happening there, what they get, if they explain it by diffusion, it's perpetual motion of the second kind, because of this water content gradient like the one I showed you with the conical pores. And he, on and on, Don Paul replied with another very, very long response with a lot of mathematics, and no one paid attention to it because maybe it was difficult to, and it was hidden, and no one paid attention, and then the solution diffusion continued to dominate until 2021. So I suggest, and again, everything is given here. If you have the comment, you just click on it and you open the article, and it's quite intriguing. Lastly, I would like to talk about the solution friction model very briefly. Again, it's beyond the. So this was the paper we published in 2021, again by postdoc Li Wang, and and we describe it in this paper in ESNT. Again, it's as I told you, it's already a highly cited paper, and here we're just talking about the principle because it's beyond the scope, and again, then we go to the conclusion. So you take a volume element, and you practically apply force balance. And the force balance, when you have a pressure gradient, which is a force, will be balanced by friction. So this is what we call friction-based models. And they're very common in modern transport phenomena. So all the driving force will be balanced by friction between the water and the membrane, FWM, friction coefficient, and the ion and the water. And delta P, the delta X, which includes also the osmotic pressure, is the driving force. And when you derive this equation for this force balance, you will have this component. You will have the component of the friction of the fluid, water, with the membrane, Fm. So multiplied by the velocity, this will be the pressure drop inside the membrane, plus another friction that is formed by the difference in the velocity between the water and the ions. Water and ions move. Whenever you have relative motion between two components, you have friction. This is the definition of friction, relative motion. For example, when you have friction, no slip boundary condition, the surface is zero, doesn't move, and the fluid moving. But if things are moving, as long as you have relative velocity, you will have some friction. So this is the friction between the ion and the water. So now we have delta P, delta X, and now we have the pressure drop across the membrane and some pressure drop or friction related to the relative velocity between the ions and the water, because you have desalination here, you have salt moving with the water. And you can now write again, this is the expression for the velocity of the ions. We can use more like an extended Nernst-Planck equation for the velocity of the ions. And you can define some friction coefficient that described in the paper and plug this VI, you plug it here. You plug it here, okay? And when you simplify, you go through any step, you get this kind of behavior. The water flux, VF, water velocity, equals to some pressure gradient, and this will be more like the friction of the fluid. But based on this equation, you also see a component of the electric potential gradient. This is the electric potential that develops whenever you have a charged membrane and you have a ion flowing through, you can get membrane potential develop across the membrane. So based on this equation, the water flux should also be affected by the electric potential gradient. Okay, so I'm putting this equation again. But how can you test this? When you take reverse osmosis membrane, which was the focus of our studies, the fixed charge in reverse osmosis membrane is very small. It's about 0.1 molar, 100 millimolar. So we said, let's take ion exchange membrane, and at this time, we did it before the recent paper that claimed that ion exchange membrane are solution diffusion membrane. So an ion exchange membrane can have charge up to 3 molar compared to 0.1 molar, or 3 or 4 molar compared to 0.1 molar of the RO membrane. So here, if you take ion exchange membrane, maybe you can see this effect, the contribution to the electric field. So again, whenever you have electrolyte solution flowing through this ion exchange membrane with a lot of fixed charges, you will have two profiles. One of them, we have the pressure gradient that we know, but also you have electric potential gradient just because of the Donan mechanism and the way it developed. So now let's see if we can do experiment with highly charged membrane, if we can see any charge effect. And again, so we took ion exchange membrane with highly charged, we did experiments and permeation experiments, and then we measured the water flux versus salt concentration. We were able to fit it by the solution friction model, the theory, very well. We did salt rejection, also was affected by salt concentration. We were able to fit the data. And importantly, when you talk about the water permeance in RO is not a function of the salt concentration, but here we see some dependence because of this contribution of this electric field that again is negligible for reverse osmosis. So we show that even for ion exchange membrane, we can use the solution friction model to describe very well transport in ion exchange membrane. Indeed, the solution friction model is more like a more refined version of the old paper by Kedem and Kachalski in 1957, I think, and so it's just a viscous pore flow model, and it can fit reverse osmosis very well. So by the way, the Kedem and Kachalski paper was a classic, and then was another modification of it by Spiegler, Kedem and Kachalski, and they derived show that it can also be friction-based model. So it's interesting historically, Aaron Kachalski was a professor at the Weizmann Institute of Israel, a very prestigious institute, and he was in his prime, writing, he wrote books on irreversible thermodynamics and even getting the Nobel Prize. But there was in 1970, early 70, was a terror attack in the Tel Aviv airport by a very crazy guy from Japan, Kozo Komodo. No one knew what, came and killed 23 people and killed this guy, but he did not even have any reason why to do it. And killed this guy that probably was on the way for a Nobel Prize, Aaron Kachalski. So now the last slide again. If you take this equation, I showed you here, you can rederive the equation that we all use for water flow. Again, reverse osmosis membrane a very low charge, so we can neglect this term here, and we can get this expression out here. Simply, we can show that we can get this expression A delta P minus sigma delta pi. And this equation for reverse osmosis, we know the reflection coefficient is 1, so we can derive this equation. And the only difference here that now the permeance is a function of the friction coefficient, not as a function of the solubility and diffusion as in the solution diffusion model. Although the solution diffusion model was able to get the same equation without the sigma, the A is completely different. The mechanism is completely different. So mathematically they're equivalent, but here it's friction, there is partitioning. So concluding remarks, surprised that I still have the energy. Okay, so all membranes are porous, RO, NF, OSN, whatever. Some are more porous, some are less porous. If you have a non-porous membrane, nothing will go through, period. Again, it will not be a membrane. So even those of you who went to my lecture before, I talked to you about the solid state electrolyte. I showed you that dehydrated, naked lithium can go through, but water cannot go through because water is bigger than the pores there. So again, so what I think the implication for us, we need to develop methods, ideally operandi techniques, to analyze membrane microstructure, pore architecture, connectivity, and so on. And we need to move to pore engineering. By designing the right pores, you can get the right membranes. Assuming that it's just solution diffusion mechanism, this is why in the last 50 years we did not make a lot of progress, because people measure only partitioning and you know, so. But we all know that pore size is critical. Second conclusion, in the absence of time-resolved operandi techniques to probe transport phenomena in membranes, molecular simulation are vital for making fundamental progress. So we need to enhance collaboration with computational scientists and take the good ones, because not everyone who can operate the software can understand the physics well. And also we need to draw on the vast knowledge from the field of nanofluidics literature, or now we call it angstrom fluidics. In the angstrom fluidics, they already show that even in carbon nanotubes that are smaller than 1 nanometer, you still can describe water transport by Navier type equation when you correct for all this viscosity, etc. Third conclusion, water solvent transport in solute rejection polymer membranes, RO, NF, OSN, IM, is governed by viscous flow or pore flow and is driven by pressure gradient. This is the equation, and the difference here that you have a friction coefficient as opposed to the solution diffusion model in which the permeates assume partitioning and diffusion here. Okay? All this apparent experimental evidence for the solution diffusion model, which is really textbook material, is flawed. I showed you that it's all by compaction. I can take any membrane, you do this experiment, all of them will show the water content gradient. If you do this experiment, you can say that all membranes are solution diffusion model, or solution diffusion type membrane, which is not the case. And lastly, again, I will not, there were some other studies that are done very, very poorly, including some from Israel, my home country, Israel, they're really with very poor science, not any simulation and everything, and they criticize, but again, I do not even need to show this slide. It's very, very poorly presented and a lot of things. So this brings me to the end. I would like to thank all the team and for your attention. Now time for questions.
Thank you very much, Mindy.
Okay,
Yeah.